Alright, welcome back now to chapter 20. This is on galaxies and the foundation of modern cosmology. So we're going to ask ourselves some deep thinking questions here. How are the lives of galaxies connected with the history of the universe? And this picture here we're going to see in a minute is of the Hubble Deep Field. So one of the deepest images ever taken of the universe was the Hubble Deep Field, and since then, this was in 1995, we have taken deeper images of the deep field called the Ultra Deep Field. And the reason you see this staircase is because this is a newer system of cameras on Hubble we put in at the time. Has a high-res camera here in the middle and then some larger, bigger arrays that are not as spectacular on the outer sides. This is part of a picture from the Big Dipper, Ursa Major in the northern sky, with a region of the Big Dipper where there are no visible stars apparently. So every single image of light you see in this Hubble Deep Field is a galaxy containing billions and billions of stars. And so we're going to talk about galaxies and cosmology. A galaxy's age, its distance, and the age of the universe are all closely related. The study of galaxies is less intimately connected with what's called cosmology. And cosmology is the study of the structure and the evolution of the universe. Cosmology. So what are the three major types of galaxies? Here's a picture from the Hubble Ultra Deep Field. Again, where every speck of image there is a galaxy. And you can start seeing some structure to some of these items. And so one kind of galaxy we have generally is a spiral galaxy. It looks like a hurricane, kind of like the Milky Way galaxy. And so we see these in the Hubble Deep Field pretty well. Billions and billions of stars. We see elliptical galaxies, and these tend to be more of an egg shape and contain older stars. And then we have irregular galaxies like we see here. These are just kind of blobs of gas and dust that make up galaxies. So in the spiral galaxy, of course, we have the disk with the gas and dust, the bulge where the black hole is in the middle, and the halo where the globular clusters of the older stars are. In the disk component, we have stars of all ages. Many gas clouds consist here in the dust and gas. And in the spheroidal component of it, we have the bulge and the halo and some old stars and a few gas clouds. So in the disk component also we see stars of many ages, many gas clouds. The blue-white color indicates ongoing star formation. The red or yellow color indicates older stars here in the middle. When we think the Milky Way galaxy, our galaxy is actually a barred spiral galaxy. It looks as a spiral galaxy with a bar going through the middle of it. You can see that here with the dust band. And here the spiral arms actually come attached to the end of the bar, not the center of the galaxy. And so we think that our galaxy is a barred spiral galaxy. Then we have lenticular galaxies. These have a disk like a spiral galaxy, but much less dust and gas. The elliptical galaxies are very old. They're all spheroidal. It can be like a basketball or an egg. Virtually no disk component, and the red-yellow stars does indicate that older star population. The irregular galaxies have a lot of blue-white color indicating lots of ongoing star formation with all these gas clouds and dust going on. And so this is Edwin Hubble's classification of galaxies. We have the ellipticals called an E. They go from the number 0 all the way to 7. An E0 galaxy is a circular spheroidal galaxy. E7 is more elliptical. And then we have the spirals, which are two kinds, just the regular spirals and the barred spirals. And they go from SA, SB to SC. SA galaxies are very tightly packed, tightly wound galaxies, where an SC is very loose arms, very loose going. It even goes to SD where they're almost broken arms. The spiral galaxies have a capital SB and then the ABC to indicate the same kind of thing. So how are galaxies grouped together? Spiral galaxies are often formed in groups of galaxies up to a few dozen galaxies. And in fact, we do have our own group of local galaxies called the local group, which is about 25 galaxies close to the Milky Way, with the Milky Way and Andromeda being the two largest galaxies in those. The elliptical galaxies are much more common in huge clusters of galaxies, hundreds to thousands of galaxies. So what have we learned here? We have learned that the lives of galaxies are connected with the history of the universe, and galaxies generally formed when the universe was young and had aged along with the universe. The three major types of galaxies are spiral galaxies, elliptical galaxies, and irregular galaxies, where the spirals have both disk and spheroidal components and ellipticals have no disk. Spiral galaxies tend to collect into groups of up to a dozen galaxies, and the elliptical galaxies are more common in large clusters containing hundreds to thousands of galaxies. Now the next question is, how do we measure the distances to these galaxies? Well, you look out into the universe and you see two stars, one is dim and one is bright. But the question is, are they far away or luminous or very luminous, very bright, or what is it? Brightness alone does not provide enough information to measure the distance to an object. But knowing a star cluster's distance, we can determine the luminosity of each type of star within it, because we assume, being in that cluster, that every star in that cluster is the same distance away from us and then formed at the same time. There's a type of star called the Cepheid variable, and they're very luminous and they pulsate a lot. They go in and out like a balloon going in and out. Cepheids are very useful to us because they provide us a tool with telling us how far away galaxies are if we find a Cepheid in a galaxy. This is one of Hubble's laws they determined. Cepheid variables with short pulsation periods are pretty close to us. Let's say 3 or 5 days, they're pretty close to us. Those Cepheids that may be more like on a scale of 50 to 100 days are farther away from us, and that's a linear scale. We have these things called standard candles. Cepheid is one of them. White dwarf supernovas can also be one of them. And a standard candle is simply a way to use that object to determine the distance to a galaxy. They are standardized. So here's Edwin Hubble, famously at the telescope from Marshfield, Missouri. How did Hubble prove that galaxies lie far beyond the Milky Way? Before Hubble came along in 1929 and decided this, we thought everything was in our own little galaxy, but then he proved otherwise. So before Hubble came along, some scientists argued that spiral nebulae, Greek for cloud, were entire galaxies like our Milky Way, while others maintained that they were smaller collections of stars within the Milky Way. The debate remained unsettled until Edwin Hubble finally measured their distances. Hubble settled the debate by measuring the distance to the Andromeda Galaxy using Cepheid variables as the standard candles. So what is Hubble's law after all? Here's Hubble's actual drawing of it. By measuring distances to galaxies, Hubble found that redshift and distance are related in a special way. And redshift is a spectral feature in those spectral lines where the lines are shifted more to the red end of the spectrum, indicating a radial velocity going away from us. Just like with radar and weather beams looking at rain, a red shift means the object is moving away from us, and the more the red shift there is, the faster it is moving away from us. And so Hubble's law is basically the velocity of the galaxy is this number called the Hubble constant, h naught or h sub 0, times its distance. Currently, the h naught value, Hubble's constant, is about 72 kilometers per second per mega light year. Ignore this 22 on the screen. I don't know where they're getting this 22 from, but trust me, it is about 72. That's probably a misprint on their part. 72 kilometers per second per mega. Oh, well, I see the issue now. It's 22 kilometers per second per millions of light years. We don't really use that term. We use megaparsecs, which is 1 parsec is 3¼ light years. So in astronomer terms, it's 76 kilometers per second per megaparsec, and more, I guess, English terms, 22 kilometers per second per million light years. That means for every 1 million light years away from us, objects are moving 22 kilometers per second faster. That's about the size of the city of Springfield. So imagine an object moving from Nixa to Willard in 1 second. And if you go out 10 million light years, then that object is moving 10 times faster, 220 kilometers per second. Pretty fast. So the distances of the farthest galaxies are measured from their redshifts. And we measure galaxy distances using a chain of interdependent techniques, including the Cepheids, supernovas, and white dwarfs. So we know now that the distance measurement chain begins with a parallax measurement that builds on radar ranging in our solar system. Forget about that. We can measure distances greater than 10 billion light years using white dwarf supernovas as standard candles. How did Hubble prove that galaxies lie far beyond the Milky Way? He measured the distance to the Andromeda galaxy using these Cepheid pulsating variables as standard candles. And Hubble's law that he decided upon in 1929, very famous, is that the faster a galaxy is moving away from us, the greater its distance. Pretty important to remember. Let's repeat that again. The faster a galaxy is moving away from us, the greater its distance. So how does Hubble's law tell us the age of the universe? The expansion rate appears to be the same everywhere in space, and so the universe has no center and no edge as far as we can tell. And so you can think of this as like an expanding balloon with dots on it. One example is that, or like a rising raisin bread. And this brings us to the cosmological principle. The universe looks about the same no matter where you are within it. Matter is evenly distributed on very large scales in the universe. It has no center and no edges. The cosmological principle has not yet been proven beyond a doubt, but is consistent with all observations up to this current date. So why then does the observable universe have a horizon to it? The cosmological horizon marks the limits of the observable universe. It is a horizon in time rather than in space. Since looking far away means looking back in time, there must be a limit, the beginning of the universe. So we know that measuring a galaxy's distance and speed allows us to figure out how long the galaxy took to reach its current distance. And measuring Hubble's constant tells us that the amount of time is about 14 billion years. We actually know it to be pretty precisely more than that. It's actually 13.72 billion years old, give or take a few hundred million years. And that was really the whole goal of the Hubble Space Telescope, was to find those Cepheids and supernovas and really pin down within 5% error the age of the universe, and we have done that 13.7 billion years old. The look-back time is easier to define than distance for objects whose distances grow while their light travels to the Earth. We cannot see back to a time before the beginning of the universe.